Hi, it's good to see you again. I'm Mrs. Gilbert and I'm here to guide you through Algebra II. We are looking at exponential and logarithmic equations this week. Last week we have done logarithms. The first week we did exponentials. We looked at their functions, and the second week we looked at logarithms and how they related to exponentials in their graph. So this week we're going to start our essential concept 2, and we might have touched a bit because we have already evaluated logarithm expressions. This week we're going to solve exponential and logarithmic equations, but we're going to start with some simple ones. All right? So let's review. So what is a logarithm? So when we are looking at our exponential, we have a base with an exponent and an answer. So when we have a logarithm, we know the base and our answer, and we're looking for our exponent. And so we write that in logarithmic form. We write it with a log, with a little base, which is subscript and small, and then our answer, or our argument for a log, is going to equal our exponent. Right? So first we're going to solve simple equations. All right? We're going to be doing this by switching between forms. This is not the only way to solve exponential and logarithmic functions, but generally, to start off, I think it's kind of the easiest. And if you want to follow along, just try to make sure that you have a calculator, right, or a slide rule, which is what's in the picture, because we're going to use that to evaluate our answers. So first of all, a simple logarithmic equation. So what I'm going to use is that if it only has one variable. So if it has more than one variable, we're going to have to do something different. But for now, if it has one variable that we're looking for, we can generally switch the forms and solve that way. So when we're looking at this logarithm, log base 2, in parentheses, x minus 6 equals 5, we see that there's one variable, but it's in our argument of our logarithm, so it's going to be hard to solve that way. So what we can do is we can switch our forms to an exponential, and then we'll have our 2, which is the small base, being raised to the answer of our logarithm, 5, and that's going to equal our argument, which is x minus 6. So from here, we just work it out like a regular equation. So we know that 2 to the 5th power is 32, and then we're going to keep the other side the same. And from here, hopefully this is middle school, right? So all we have to do is move that 6 because we want the x by itself, and then we get x equals 38. One thing that we do need to do is we need to make sure that when we plug in 38, that our argument is not negative. So if we plug in 38, we get 38 minus 6, which would be a positive 32. So we are okay. Because if we made a negative in our argument, then we can't use it, and then there would be no values of x that were available. All right, so we're going to try another one. This time I want you to think about what is our base and what would our exponent be when we switch our forms. Well, hopefully you got 3 to the 4th power, and then our argument is 5x plus 1. So we get 3 to the 4th power is 81, and from here it's a regular multi-step equation. Subtract 1 from both sides, and then we're going to divide by 5. And we get 16. All right. This one, we're going to go the other way. We have an exponential with our exponent having the variable. And yes, there are other ways to solve this, but I find that this could be our easiest way. So we're going to take switching our forms, and we're going to create a logarithm. We get log base 9, 81 equals 2x minus 6. What we're trying to do is we're trying to get that exponent kind of available for us to be able to use. Right now it's in the exponent. It's kind of hard to figure out what it is. So we know that what power of 9 gives us 81, and hopefully you know that's 2. So 2 minus 2x minus 6. It's a regular multi-step equation. So we're going to add 6 to both sides. We get 8 equals 2x, and then we divide by 2, and we get x equals 4. when we plug this one in, we don't have to worry about whether it's positive or negative. So you don't necessarily have to check for that in these cases. So let's look at this one. We have one variable, it's in the exponent. So let's try switching our forms. We get log base 7, 15 equals 9x. Now, if you have a nice calculator where you can change the base and put in an argument, you're good. But a lot of you don't have that. If we have a basic calculator which has a log button and you're like, I have a log button, but there's no way to change the base. Hopefully you'll remember that that was our common base, and so that we know that all those bases are 10. So we can still use your calculator to get this answer. We can use the change of base. All right, so I know it looks a little complicated, but I'm going to walk you through it. Okay, this is so we can use our calculator, which has a log with a base of 10 already programmed in, so you don't have to worry about changing the base. You don't have to worry about what the base is. So the first thing you want to notice is that this, on the right-hand side, so we have our problem on the left, and we're changing it to the thing on the right. And the reason we can do that is because both of these are the same. So we can use our log button for the top, for the numerator and the denominator. All right? And when we do that, we're going to take the log of our top number and divide it by the log of our base. Sorry, log of our argument in the numerator and the log of our base in the denominator. Right? So I'm going to go through one that's kind of, you should already know, right? So we should know that 8 to the second power is 64. So if you put this in our change of base, we can say that the log base 10 64 divided by the log base 10 8, which on your calculator is just our log button, and then 64 divided by log 8. You should get 2 when you try it. So if you have your calculator handy, I'd like you to try it. The one thing that might be a little bit different is if you have a Casio. Sometimes, I believe the Casio will sometimes make you put the argument before the log. So you will need to make sure that you put parentheses and then your 64 log button, close your parentheses, divide parentheses, 8 log button if you have a Casio. They're just a little different. All right, so hopefully you got 2. I'd like you to try this one and make sure that you can get the same answer. All right, I do have some more because I kind of want to look at what's going on, and hopefully you can kind of see some patterns. Right, so log 49, 7. Hopefully you should know that it is 1/2 or 0.5 if you're trying it in your calculator. Right? So you should get approximately 1.95 for log base 4, 15, or the log base 10, 15 over log base 10, 4. All right. You can also get negative answers, which we talked about before. You can still get them when you're dividing. Right? And then we have log 73 divided by log of 100. All right, so now we can finish our problem, just in case you forgot. So we had 7 to the 9x power equals 15. We switched our forms to log base 7, 15 equals 9x. And so now that with our change of base, you can put this in your calculator. So we can take the log of 15, divide it by the log of 7, and we know that that's going to equal our 9x. So we know that 9x approximately equals 1.4. And then we can divide both sides by 9 and get an approximate answer. Right, so we're going to take this knowledge and we're going to work towards some word problems. So it's going to take us a little bit to get there, so keep with me. All right, So if you remember our models for exponentials, we had a y equals a with a base and then an exponent. Okay, so our initial amount is the a, right? So this is the amount that we're starting with. The number of cycles, which is going to be our exponent, and it's going to be the same rate, same units as our rate. So whatever our rate is in, that needs to be the number of cycles, how you calculate the number of cycles. So if it's per year, you need to put how many years. If it's per day, you put how many days. Right? And then we need to know if it's growth or decay. So remember, b will be greater than 1 for growth and between 0 and 1 for decay. So b is not going to be negative, and it's not going to be 0, and it's not going to be 1. So just make sure that those are not going to be your answer, your b's. All right, so our factor is our base, and our rate is usually done in a percentage, so we're going to need to change that to a decimal. So if they give you a rate in a percentage as opposed to a factor, then we need to make sure that we change it to a decimal. So if it's growth, we're going to add 1 plus our rate divided by 100 because the rate is given in a decimal. I mean, we need it in a decimal and it's given in a percentage. And our decay is going to be 1 minus our rate over 100. So we're going to start with a model. I want you to look at this model and see if we can figure out what each piece is. So hopefully, first of all, we have our cycles. Our cycles are going to be the exponent, x. And here we don't have a rate because it's not given, right? So our initial amount is the 532. And which one is the factor? So that's going to be our 1.58. That's our base. So we're looking at this. Do we know if it's growth or decay? So if you're looking at your base and it's bigger than 1, you know that it's going to be growth. And if it's smaller than 1, it's going to be decay. So 1.58, bigger than 1, it's going to be growth. Now this one is a little tricky. We're going to have our rate. So I rearranged our formula a little bit. So we know that growth, our b equals 1 plus r over 100. So when I rearranged it, we get r equals 100 times b minus 1. Right? So 1.58 minus 1 is 0.58 times 100 is 58%. Okay, so let's try this one. So cycles, again, is our exponent x. We could also use other variables. Our initial amount, 891, and our factor, 0.82. Now, is it growth or decay? Decay, because it's smaller than 1. So now we're going to look at our rate. So when we're doing a decay, it's going to be a little bit different than our growth. So decay, we have 1 minus r over 100. And I rearranged it, and it ends up being 1 minus our base. All right, so we take 1 minus 0.82, we get 0.18, times 100 would give us our 18%. Now this is going to go with the decay part, so that's why it's a minus 18%. Okay? So now let's try, given some givens, to create our model. So if we're given 1,500 and a rate of 7.5%, and we know that it's growth, so first of all, I'm going to set up our model. So I have a y equals a space with our parentheses, and where are we going to put everything? All right, so 1,500 is going to go in that initial spot because it's not being affected by how many times we're sorry. It's not being multiplied by the cycles. It's an initial amount. So then we're looking at the cycles, which needs to be in number of years because our rate is in number of years. All right? So we have a growth of 7.5%. And so when we plug this in, you get 7.5 divided by 100. Now I know some of you guys are going to miss this 0, so I want to make sure that we pointed it out. So when you're dividing by 100, you're going to get 0.075, right? You're not going to get 0.75, okay? Make sure that 0 is in there. And then we could plug that into our model. All right, so let's try another one. So for our initial amount, we are given 3,123. We have our rate of 21% per year, and we know that it's decay. So when we're looking at this, we're going to plug in our initial amount outside of our parentheses. Right? And then we're going to know that our cycles are going to be in the number of years, and that's going to be our exponent. And then we're going to use the rate and whether it's decay or growth to figure out our factor. So we know that b is going to be 1 minus r over 100. So we're going to take 1 minus 0.21, and we're going to get 0.79. And we're just going to plug that into where our parentheses are, because that's what's getting affected by the times that we are going through the cycle. All right, so one more thing before we get to our word problems. I wanted to make sure that you knew what kind of growth or decay words are there. So these are the words that are going to be associated with our rate or our base words. All right, so if it's growth, you're going to see growth. Sometimes you'll see double or triple. And these are going to affect your factors, and you probably won't have a rate with those two. You have rise or appreciate, increase, and sometimes you'll have uninhibited growth or continuous growth, and your base is going to be an E in those cases. So if you haven't gone over E, we will be going over that soon. And then we have decay words. So we have decrease, or down, or drop. You can have half-life, which sometimes will be actually 1/2, and sometimes it'll be an E. It'll depend on the situation. Lower, loss, or less, and depreciate or depreciation. I really want to emphasize the appreciate and the depreciate because some of my students haven't heard of these words before. So I just want to make sure that you know that appreciate means growth and depreciate means decay. So for our first example, we are going to have the foundations of your house has 1,200 termites, and these termites grow at a rate of 2.4% per day. So how many termites would you have in a week, and how long would it take for this number of termites to double? All right, so this is a little crowded, so hopefully it'll give you a chance to look at everything. All right, so I have the word problem on the left, just to make sure that we can still see it. And then right next to it, I have our given. So we're going to write down what we're given in our word problem, and then we're going to create a model, which is space underneath our word problem. And then we're going to work out our two problems on the bottom of the page. All right? So I want you to think, what is our initial amount? What is growing? So our initial, oops. Sorry. I missed that. Sorry, it should be 1,200 termites. All right. We have 2.4% per day. And we're saying if they grow at a rate, we're increasing the number of termites. So it's going to be growth. And then we're going to have our cycle, which is going to be our exponent, but we need to know our rate. So it's going to be in the number of days because our rate is in days. So we always need to make sure that those two match. And then we're going to use our rate and our knowledge that it's growth to create our factor. So we're going to get 1 plus 2.4 over 100. And we're going to get 1.024. All right, so I know that there's a mistake that it should be 1200 instead of 120, but I did do it in our calculations. I just missed it in our model. All right, so we know that when we're looking at how many termites do we have in a week, you should know that 1 week is 7 days. And so we're going to plug in 7 into our model, which is actually 1200 times 1.024 raised to our to our exponent of 7. And then from here, we'll just work that out. So when we raise 1.024, you should get 1,417 termites. All right, so how long does it take to double? So we're going to need to know, so now we know how many we have at the end, right? That's going to be 2,400. And we're going to plug that in for a y. And now we're going to look for the number of cycles that we're going to go through. So we're going to switch forms, which did move. All right, so we'll get, when we divide 2,400 by 1,200, we'll get 2. Sorry, now we're switching forms. And then we'll have our base of 1.024 with an argument of 2, which we could write, if you don't have a calculator that will do that as it is, you can change it to log 2 divided by log of 1.024, and we should get about a little over 29 days, or 30 if you're rounding up. All right, so let's go through this one quickly. So if we drink coffee with 120 milligrams of caffeine, so each hour the caffeine in your system decreases by 15%. How much is your caffeine is in your system after 3 hours? And then how long until you have 10 milligrams of caffeine in your system? All right, so again, we're going to look at this. Our initial amount now is 120 milligrams. Our rate is going to be 15% per hour, right? So we're looking at this. Decreases, right? The amount of, you're kind of using this caffeine, it's decaying, right? So it's going to be decay. Our cycles are going to be related to our rate, so we need to make sure that it's in the number of hours. So, and then we're going to have our factor, which is going to be 1 minus our rate divided by 100. Now that's only if the rate is in percentage. All right, so we're going to get 0.85. Now I'm going to go kind of quickly because I'm getting the signal. So we're going to plug that into 0.85. So how much caffeine is in your system after 3 hours? Well, this one's a little bit easier because our rate is in hours, so we know that our cycle's in hours, so we can just take that 3 and put it in our exponent. And we go through and we get 73.4 milligrams. And then how long to get to 10 milligrams? So y is how much is left in your system, right? So we know that 10 is going to be the amount left, and we're looking for our x. So we're going to divide that, and I wrote it in a decimal form, but you can keep it in fraction form if you want to. All right, and then we're going to switch forms because it isn't an exponential, and we only have the one exponent, so it's really pretty easy to switch forms. And then we can plug that in our calculator, and we get about 15 hours. All right, so to wrap it up, I want you guys to be thinking about switching your forms for solving, that you need to know the change of base, and then modeling. We use the rate to find the base, and it's usually percentage, so we need to change it to decimals. And then our base words, especially appreciate and depreciate. All right, it was good to see you, and I hope you guys have a good week.